What's up guys, Randy with Fix My Heat again. We're going to be talking about capacitors today, what they are, where they are, what they look like, how to diagnose them, and how to replace them. These are some of the typical capacitors that you would see in a residential or light commercial application. We've got a single capacitor here. It's only got the two terminals on the top of it. We've got a dual capacitor, another dual capacitor, and then this one is a multi-capacitor where you can pick a size. We'll get to that in a moment. This one, the single capacitor, is rated for 5 microfarads. What you'd most likely see this installed on would be a residential blower motor, even some light commercial blower motors that are 120 volts to that motor. This one is a 5 microfarad plus or minus 5%. So if we were to take a capacitance meter or test the microfarads of capacitance that this holds, we would see that it'd be right around 5 plus or minus 5%, assuming that it's a good capacitor. This is rated for 440 volts AC alternating current, so we can put up to 440 volts AC through here safely. This one is a dual capacitor. It's rated for 40 microfarads and 5 microfarads. So if you look at the top on this one, you'll see that this one here is labeled C, this one's labeled Herm, and this one's labeled Fan. This C terminal is shared between these two, and what we essentially have is two capacitors, one here and one here, with a common terminal between the two of them. So this is two capacitors, one here and one here, at two different sizes, 40 and 5. And what you'll generally see this installed on is going to be your condensing unit outside. If you've got a split air conditioning system or even a HVAC unit on a rooftop, you might see a dual capacitor installed rather than two separate capacitors. This 40 is normally used to run the compressor, and then this 5 is normally used to run the fan, the condenser fan motor. You'll see that this one also says it can run up to 440 volts AC. This one is the same size. It is a 40 by 5 microfarad capacitor. The only difference between these two is this one is a Total Line brand, and this one is a First Choice. So if we look at the Total Line again, we've got the 40 plus 5 microfarad capacitance, so it's got the two sides to it. And this one says 370 to 440 volts AC. So you'll see different dual capacitors on the market. Some will just say 370, some will just say 440, and some will say 370 or 440. You can always replace a 370 with a 440. You should never replace a 440 with a 370. If it's got a 440 in there designed from the factory, from the manufacturer of the unit, you should always replace it with a 440. But this one says it can do both, and that's just because it's actually a 440, just like this one is. But they didn't want technicians to get confused and think they needed to run to the supply house to go pick up a 370, because this one can be used on a 370. Then this one here is called the Turbo 200. AMRAD makes these. It's an American-made product. It's a really cool product because it's a multiple size capacitor. It's got a common here in the center, just like the common terminal on this guy here, and multiple taps around the outside that are rated for different capacitances. So this one's a 10, this one's a 20, this one's a 25. If I needed a 30 microfarad capacitor and I didn't have one on the truck, I only had these 40s, then I would put a jumper included in the kit between 10 and 20, hook my Herm wire up to the higher of the two, the 20, and now I've got a 30 microfarad capacitor right there, because that is being shared against that common. And then that third wire would go to, say, the 5 microfarad, or maybe I've got a jumper between my 5 and my 4 here so I can get a higher capacitance for my condenser fan motor as well. This also has a CPT terminal, which is for hard start kits. If you had a start capacitor on the system, we'll talk more about that another day. So here's a description of how a capacitor functions. In this circuit that I drew here, it's a pretty simple circuit. We've got a battery that has a positive and negative charge. That battery has 1.5 volts or something in it, just like a AA battery. And there's a wire coming out this way and a wire coming out that way, and they connect to a capacitor, and that's this symbol right here. So imagine the capacitor exactly how you see it, 2 plates with space in between. There's an insulator in between these plates. And what happens is this negative charge wants to get to this positive charge. It wants to travel to it. It can't go through the battery, so it wants to go this direction. So it'll go this way and build up on this plate here. So we've got a bunch of negative charge on one side of the plate, which inherently means we've got a bunch of positive charge on that side of the plate. So now we have capacitance between those two sides. We have stored energy, similar to the battery, stored energy. So if we were to reverse this polarity, put negative here, positive here, now all this negative energy wants to run around this direction, and you'll get negative buildup on this side and positive buildup on that side. So alternating current, like you have running on the wires in your house, will do that. It will swap back and forth between positive and negative current, back and forth. So those electrons, negatively charged electrons, rush back and forth through that circuit. Think of the capacitor like a balloon. You inflate the balloon, and then you can deflate the balloon the exact same amount. So you can fill it up to an exact amount. If you try to overfill it, it might pop, similar to a capacitor. There's only a certain amount that that balloon can hold, and then when it deflates, there's only a certain amount of air that can come back out of it. That capacitor can only hold so much charge, and then it can only discharge so much. Your standard house current is 60 hertz. 60 hertz means 60 times per second. That's the frequency that your alternating current is shifting back and forth. So we have 60 times a second, this capacitor is charging and discharging. You've got an inrush of electricity going into the capacitor and staying there, and then an outrush of the same amount of energy coming back out. That is used to phase shift or offset the amount of electricity that it stores to go back into the motor during the off cycle of the phase. So when the power comes in from the utility, it uses it to push the motor. When the power comes back out from the utility, the stored energy is used to push the motor again. So this can be used to help keep a motor running when the rush of electricity isn't there anymore from the alternating current from the utility. Now we know what a capacitor looks like. Generally speaking, you're going to find them near the motors that they're operating. So look near the blower motor inside the furnace to look for a single capacitor. Look if you're looking for a dual capacitor in your outdoor unit. It's generally going to be in a side panel where the electronics are, and you're going to be looking for something similar to this. Now, what's inside of a capacitor? If I could open this up for you, which I won't because this one's brand new, you'd see a coil inside of there of what looks like tinfoil, extremely thin tinfoil. And that's wrapped around the inside of the capacitor in a very tight loop. But just like the picture I drew a moment ago, it's actually 2 conducting metals, one on each side of the other, and an insulator in between, so that energy can't travel from one side to the other. The energy built up on one side can influence the other side, but it can't jump the gap. There's an insulator in between that's keeping it from doing so. So if you were to unwrap this capacitor and pull it apart, this foil you'd see is actually 3 layers. Got a layer of the foil, and then behind it there's a layer of plastic, and then behind that is, or some sort of other insulator, and behind that is another layer of foil. So we start to build up a charge on one side and the opposite charge on the other side. So you get negative charge on this side and positive charge on that side. Now, if at any point this insulator in between fails, then you lose capacitance. Now the energy can actually travel through there. If the energy can travel through there, then it can't store the energy it needs to push your motor. And if you can't store that energy, chances are you won't even be able to start your motor. Your motor will lock out on locked rotor amps. It'll attempt to start and then overheat because it doesn't have the energy to push that motor, to get that motor up and spinning again. So what causes a capacitor to fail? Well, not being sized correctly is a good way to make a capacitor fail. You don't want to oversize or undersize a capacitor. If you had a 30 microfarad capacitor hooked up to that compressor before, you should put a 30 back in. I've heard technicians say it's okay if you oversize it a little bit, don't ever undersize it. Don't oversize it either. Get the right size capacitor or use 2 capacitors to make the right size capacitor, and we'll talk about that in a moment here too. A lot of times what you'll find is a failed capacitor accompanied by a failed motor. Chances are the failing capacitor is what took out that motor, whether it be the compressor, condenser fan motor, blower motor on the furnace. If a capacitor isn't up to its rated capacitance, it's no longer supplying that motor with enough energy to do its work. That'll cause the coils, the copper windings of the motor, to actually get hotter because they're trying to do more work that they can't do without that capacitor in place. So that'll wear out the motor faster. I've heard technicians say, well, that motor went out, so it looks like it took the capacitor with it, when in reality, it probably was the other way around. The capacitor was starting to fail, nobody checked it in a few years, and that's what took out your compressor. That being said, we need to find a way to test the capacitor. The best way to test a capacitor is when it's under load. So with the air conditioner or blower running, we want to simulate what it looks like when it's actually operating, when it's heated up from operation, when it's been running for a little while, so that we know what the capacitor looks like, not when it's cold and in our hand, but when it's hooked up to the equipment and operating. And the best way to do that is with this math formula. And once you get it memorized, it's actually faster to do it this way than to power down the equipment, pull off the capacitor, and put a capacitance meter across the contacts. That might be more simple in your mind, but this is going to be much faster if you're running tune-ups. So you're going to take your amp clamp and you're going to hook the Herm wire through your amperage meter, and you're going to get that amperage. So we're going to do a test one here right now. We're going to say that that was 4.6 amps is what that compressor's pulling across the start winding on the Herm terminal. And yes, the Herm terminal is connected to the start winding on your compressor. And then let's measure the voltage between Herm and common. And we'll say that that voltage is 319 volts. Now, that sounds like a weird number, but that's probably a number that you'll see pretty commonly. You're not just going to see the 240 volts from the utility, you're also going to see back EMF from the motor running. The motor is magnetized and the coils are copper. So the coils are spinning the magnetized motor, and the motor is also spinning and creating its own magnetic field. So you're going to see some extra voltage being generated by the compressor or fan or blower motor running, and you're going to see that extra voltage across these terminals. So we'll say 319 volts just as an example voltage. Now if you get out your calculator and do this quick math here, we'll see exactly how many microfarads of capacitance this capacitor is holding. You're going to take 2,652 times the amperage and then divide it by the voltage. The best way to remember 2652 is 52 is 2 times 26. So just remember 26 and then times 2, 2652. Some people will tell you that you need to do 2653, 2654, 2650. 2653 is technically most accurate, This one's easier to remember. If you want to be pure about it, you can do 2653. It doesn't really matter. It's going to throw off your calculation by a decimal point. It won't matter when you're doing the math. So 2652 is what I recommend. Times your amperage is going to be 4.6. Your voltage, which is 319 volts. All right, so this is 12,199.2 on the top. That 2652 times 4.6 is 12,199.2. And if we divide 12,199.2 by 319, then we're getting roughly 38.2 microfarads. So if that's a 40 microfarad capacitor you just tested, it's a little bit low. I don't normally recommend changing a capacitor unless it's more than 10% out of tolerance. And you'll see that this number will be different than if you were to just hook your leads up here and test the capacitance with the capacitance meter on your meter. And it's likely that's because it's got such a low voltage through the capacitance meter that it's just a different calculation than what you're actually seeing under load. And some people think they run this and they get a different number. They think, well, it doesn't work. No, it has to work. This is how electrical theory functions. This is how the electronics have to work mathematically. So if you do this, not only is it more accurate, but you can do it a little bit faster during a tune-up where you don't want to power the equipment down, especially on units that are hard to get to the disconnect or somebody didn't install a disconnect. All right, so we'll do one more as an example just so we can make sure that we've got it down. We're going to measure the amperage on our Herm wire with the unit running. And we'll say that that's 6.1 amps. And then we're going to check the voltage right here between Herm and common. And this time we're going to say 270 volts. So we're going to take 2652 times 6.1 divided by 270. 2652 times 6.1 is 16,177.2 divided by 270 is 59.92 microfarads. So better hope that's a 60 microfarad capacitor you're testing there. If it was, then you're all good. If it's 10% off in either direction, I recommend replacing it. It's very rare, very, very rare to see a capacitor increase in capacitance over time. It's almost impossible to do this test and see it raise. I have seen it, but it's more likely that as those plates start to fail, remember we drew that picture of the plates inside with the negative charge. It doesn't really look like negative charge, and the positive charge on this side. As this plate in here starts to deteriorate, it loses capacitance. That voltage is allowed to travel across here instead of being held back by that insulator. That causes the capacitance to drop, and this number will start to get lower. If that number gets lower than 10% off of the rating on the side of the capacitor, then you could do some irreparable damage to the windings on whatever motor it's connected to. All that math is way too much for me. I don't feel like doing it. What's an easier way for me to comprehend? All right, this is a meter. You're going to set it to microfarads. There's a symbol right here. The symbol right there looks just like what I drew on the board a moment ago. That means capacitance in microfarads. So I'm going to go to that setting. Got our capacitors here. Need to disconnect the wires from the capacitors so that what we're measuring doesn't go through those wires. We're going to hook our probes up. We'll start with this single capacitor here. So with the single capacitor, we've got the meter set up. It says that it is 5.054 microfarads, which is good because that's what it's rated for. Now the dual capacitor, we've got two capacitors to check because it is two capacitors. So we'll connect up to the Herm and common terminals first. Measure that, arguably the most important of the two, because it's the higher of the two, and that's what connects to the compressor. We're measuring across Herman Common right now, and we're seeing 40.46 microfarads, which that is, again, 48, 47. It's moving, which is exactly what we're looking for on this because it is rated for 40 microfarads. It's definitely within 5 to 10% tolerance there. So now you can leave one of those two connected and connect to the other one. And we have 5.001. Both of these capacitors tested good. So that means that they're safe to use on your customer's equipment. In the event that you don't have the right capacitor on your truck and you've got an important client with no cooling, there are ways to double up capacitors. You can actually put two capacitors together and reduce their capacitance, and we will talk about that right now. So the first and most commonly used way to double up capacitors to change their capacitance is in parallel. So you're going to use two jumpers to connect these two together. You're going to have one jumper from here to here and one jumper from here to here. These are just single capacitors right now, but if you needed to do it on a dual capacitor like we just talked about a moment ago, you can do it with this. So let's say this one's a 5 microfarad capacitor and this one is a 10 microfarad capacitor. If we put a jumper between these two sides and then connect these two leads to the motor, that motor is now getting 15 microfarads of capacitance because they're adding together when you wire them in parallel like that. If this was a 10, then you'd have 20, etc. If you need to reduce the amount of capacitance and you have two capacitors to do it, there's a way to do that as well, and you wire them in series. I've drawn up an example of what it would look like to see two series wired capacitors. We've got a wire coming in from the motor, one capacitor, I rated these at 5 microfarads each, a jumper in between the two, and another wire coming back out going to the unit. So we don't have that parallel jumper in this scenario. They're daisy chained together. So we've got capacitor 1, capacitor 2, and the math formula for this is 1 divided by 1 divided by C1 plus 1 divided by C2. So if you remember your order of operations from high school, C1 is 5 and C2 is also 5. So we've got 1/5 plus 1/5. That's 2/5 or 0.4. So then 1 divided by 0.4 is 2.5. So we've turned two 5 microfarad capacitors into one 2.5 microfarad capacitor. Now you might be saying, Randy, that's easy. You just tie two of them together and it cuts it in half. Well, that works if they're both the same size, but we can make it more complicated. So in this new example, I've got a 5 microfarad capacitor and a 12.5 microfarad capacitor. We put those into our math problem here. We got 1 divided by 1 over capacitor 1, which is 5, and then 1 over capacitor 2, which is 12.5. So this one we know is 0.2, and this one is 0.08. Yes, I used a calculator because I don't know. So you add those together, you got 0.28. So the bottom part of this fraction is 0.28. And 1 divided by 0.28 is 3.57142857. You get the idea. I did that in my head though. That number is our new capacitance with a 5 and a 12.5 hooked in series. So if you needed a 4 or 3.5 microfarad capacitor, you could make one to get somebody through an evening. This would probably work as a 4 if you needed to get a client through the evening. or you could put it in the place of a 3. It's a little high if you needed a 3, but nobody carries a 3 microfarad capacitor on their truck. This is a great way to do it. Or you could just carry an AMRAD Turbo 200 on your truck. This is the dual capacitor multi-size unit. They also make a Turbo 200 Mini, which is for blower motors and smaller appliances. So you've got different size capacitors in there. So if you needed a 4 microfarad, a 3 microfarad capacitor, you can have one of those on your truck in multiple sizes. I highly recommend these. They are not paying me to tell you this. This is a lifesaver if you are installing capacitors for a living. Having a Turbo 200, 200 Mini, and a 200X on your truck will save you so much time running to supply houses to get random sizes. There's no way you can keep every size capacitor on your truck. These are every size capacitor. And they've got a 5-year warranty, so really when you tell your customer, I put a Turbo 200 on there, you could say this one has a 5-year warranty, which is better than the one that I could have put on for you that would only had a 1-year warranty from the manufacturer. This one has a 5, so you're welcome. All right, guys, that's all we got for today. Hopefully you learned something. If you think I missed anything or want to expand on the subject or just want to tell us what you did learn, hop on down in the comments and let me know. Also, if you have any HVAC related questions, go ahead and ask them in the comments. Even if it seems complicated, even if it seems stupid, go ahead and ask. I would love to film an episode all on the questions that you guys have for me. So if you do have anything, hop on down there. Also, if you enjoyed this video, consider subscribing, leave a like. I greatly appreciate that you guys are here watching my content, and it's important to me that as many people see this as possible, because I really think that all this information is out there for anybody to learn, and if you can get the knowledge and absorb it, you can really do an HVAC trade or an electrical trade by just learning these things online and getting in on the ground floor of a company. But really, that is it. Again, I hope you learned something. You guys have a great day.